Okay, so remember the power rule. The power rule states that if you have a power term, x raised to the n power, what you need to do is move the power to the front, drop the exponent by 1. That's it. Move the power to the front, drop the exponent by 1. So if you have a constant multiple like 3 or -2 or whatever, 2 or 3 here, fine. It just comes along for the ride. It's not a big deal. So when I look at example 12, part A, the way I want to see this is I'm going to keep the 3 where it is. That -4 is going to roll to the front. So times -4 times x. I'm going to drop the exponent by 1. Exactly. Final answer, -12 over x to the 5th power. That's it. Does that make sense?
Would you write it like -12 over x like this, or when it's writing -12 that's the next?
I don't care actually. If I do ask multiple choice questions, I'm going to put more multiple choice questions on our next test because it gets you guys kind of more into groove of AP style type questions. Um, it just might be presented in this way. Just make sure you know what to do. But yeah, I don't care. It doesn't matter to me. So for part B, what should we do now? What would that be? 4 over x cubed. Because x is -3, so it comes 4 over x cubed. Okay. And then for part C, you have two different things, but because there's a minus in between, you could do each one individually. That's one of their derivative properties. So that should be 14x6. And I'm going to do this in my head, but I could make a mistake. Let me know if you disagree with me. You can totally disagree with me if you want, but I think I'm right. That's because we have -3x over x6. That's -3x -6, which is 18x -7. Cool. All's good. Sweet. Okay, any questions? All right, let's keep moving. Uh, Now here's where it gets a little funny. Um, this is a precursor to another rule we'll talk about not until next month in March, or talk about chain rule. But u of x is some equation that has x in it. I don't know. It could be some weird thing. It could be x squared or tangent or e to the x. I have no idea. Likewise, with v to the x. So u is not x. V is not x. Yet you're being asked to take the derivative with respect to x. So this right here means we're taking the derivative with respect to x. But you don't see any plain old x's in the expression. So when you write it, you write it like this. 7 um, times u prime minus 3 times v prime minus 5 u prime v plus u v prime. The problem is that I don't know. I can't just leave it like this, right? Because we're taking with respect to x. And you're told that, hey, you, if your the vertical functions in terms of x, u of 5, we do this at 5, by the way, is 10, u prime 5 is 1, v prime 2, v prime 5 is 3. So if I think about it, that'll be 7 times -1 minus 3 times 3 minus 5. That's -1 times -2 plus 10 times 3. Okay, cool. Okay, questions? I'll come back to you guys, hopefully. And what rule did I use for that last part? 5 UV. Well, no, we did product rule. We're not doing any power rule because I had no exponents. I mean, sure, if u of x is a polynomial and I had to kind of do that derivative and figure that out, sure, I would do that, right? But I had no exponents in the problem itself, so I just did product rule for the end. So you get negative 176. Okay, why don't you guys try part B on your own? Part B is using the same differential functions u and v. Going to give that a shot. So using quotient rule. So check your notes. You have quotient rule. I'm going to do it as well. I'm going to freeze the screen. We'll check in about 2 minutes.
Wait, for the test, you would memorize the book in front of them, or they put
Oh,
up.
yeah, you got to know.
Oh.
Yep. I do not give that. You're expecting to know that. You guys have an answer? What are we getting? Say, okay, you got it. You got it. Good work. Yeah. Good. Yeah, 725. There we go. So product rule. You get 20 over what? Got it. That's mad. And actually, you don't have to simplify, by the way. On the AP exam, they actually prefer unsimplified answers on a free response question. They want to ask, this is too easy for a free response, by the way, way too easy. But in general, you don't have to simplify. You can leave unsimplified answers. It's totally fine for free response. So I would too. Okay, next up, second higher order derivatives. Second derivatives actually do matter. We'll have that discussion later in the semester, why it matters. But for now, we're just going to just take the derivative twice, just to work out mechanically. That's all. So f prime of x is easy. Hopefully, you guys see it's 8x cubed minus 15x squared plus 22x minus 5. So can we take the derivative again? Of course. Why not? Just do it again. 24x squared minus 30x plus 22. So the derivative, we kind of think of as dy over dx or y prime, is called the first derivative of y respect to x. And the first derivative may itself be differentiable as well, meaning you could do it again. And if you do it again, can I move the screen? Okay. Yeah. If I do it again, it could look like this. There are a few ways it could look. You could say d dx of dy dx. So what you're doing is this is like saying, I'll put this in the text box. It's like saying the derivative with respect to x of the derivative of y with respect to x. And what you're doing is you're kind of trans that's not good. Let's fix that. Because the derivative with respect to x, that's what the first part is, d of dx. Of the derivative of y with respect to x. So that's how you say it. So basically you just do the derivative twice. Sometimes we write like this also. This is a very common way of writing it. Why it's written this way, I don't really know, but it's kind of weird. D2y over dx squared. That's no way of writing it. Y is a square next to d in the top and next to x in the bottom. I'm not 100% sure. But if you see that, don't freak out. It just means second derivative. That's all it means. Sometimes we like to write like this. I kind of prefer that. F double prime x. Write like that too. So it's yet another way. So um, so hopefully it makes sense what's happening there. So the second derivative itself may be a differential function of x. If so, its derivative um, is continuous. Because if you can take the derivative, then we know continuity exists. So it means the derivative itself is continuous. So if you graph the derivative function, that derivative function is going to be continuous because then you could do derivative again. So for example, give me an equation for this guy. Y equals x squared. Okay, give me its first derivative. 2x, which looks like this. Ah, now, is that derivative graph 2x, is that continuous? Sure. So give me a second derivative. 2. What's that going to look like? Just line. I can even do a third derivative. What's the derivative 2? And of course, that would just be on the x-axis, right? Can I do the fourth derivative? Still 0. And then all the future derivatives? Still 0. Yeah, totally. So you can do this over and over again. Ultimately, you're going to have to get down to 0 if it's a power term with a positive exponent or whole number exponent. Let me rephrase that. So yeah, okay. So sure, can you do a third derivative? Why not? Right? It looks like this. D dx. She's really loud. Getting very passionate. The things that compounding interest. It's actually a fun problem to do. Anyhow, yeah, you're just doing it like three times. Like, I gotta do this, I gotta do it again, do it again. Or I prefer to write like this. I don't know why there's all these different equal signs, but anyhow, it looks like this. Oh, sorry, got mixed up. My apologies. And so on. So there we go. And by the way, you can also write as f triple prime of x. From a physics perspective, we don't care about third derivatives. Third derivatives are actually kind of pointless. We rarely even broach that. Second derivative, we do, but don't worry about that. But just so you know, first derivative is what here? Hmm? Next up, next up, correct like that. Now, notice that there's all these like markings here that can get very cumbersome. What if I ask you for the 10th derivative? That'd be kind of crazy, right? I wouldn't ask that. That's kind of stupid. But here's what you could also write as. I kind of forgot to mention this. You could also write it like this. Um, I know my threes are terrible, but if you write it like this, that actually indicates a third derivative. Where you put it in parentheses, put as a superscript above that. That would indicate that I'm doing the derivative 3 times. If you write it like that, you're not raising to the third power, mind you. If you're raising to the third power, you actually put a bracket and raise to the third power. So it's not this. Please don't confuse it with this. It's not that whatsoever. So pretty straightforward stuff. Okay, let's talk about piecewise functions. differentiability here. So is it differential at x equals 0? What's the first you should always check? Good. Always check continuity first. So, what's f0? Right? And let's find the left-hand derivative, which is what? And the right-hand derivative? You guys see I got the left-hand derivative, right? I plug back into the top function. Do you guys see that? Cool with that? So the limit as x approaches 0. So condition 1, condition 2. And then, of course, the third condition is also true, right? So now how do I, so we're good there. So what's the next step? You guys remember?
On the left.
Yeah, left right hand derivative is correct. That's going to be 2x plus 1 for left hand. Right hand's going to be 3. So the left hand derivative is going to equal 1. But it only equals 3. So those are not the same. So f of x is not differentiable at x equals 0. Good? Yeah, all right. I think that completes that part of the notes. So my plan is to see how far we can get. So it's got plenty of time. So I know I'm kind of doing a big dump here of information, but hopefully that was okay. It wasn't too bad. That was pretty reasonable. So now we're going to talk about application of derivatives. My plan is to get to the middle of this page here. I don't want to do example 2 because I think that's best saved for an Wednesday. And then the notes on Wednesday is going to be pretty straightforward on trig. Trig is actually pretty easy. Um, and if any leftover things, we could cover that on Thursday anyway, but trig is pretty easy. I'm not too worried about that. Okay, so let's talk about linear motion today. All right, here we go. So, so remember, slope, right? Slope's a big deal. So we could think of, when we think or calculate a rate of change, we are comparing two quantities, right? We're comparing the rate of change of y to rate of change of x, right? So change of y is the numerator, change of x is the denominator, right? What this means is that how much y changes some amount of change in x. For example, if you have 3/2 of your slope, this means that for every +2 increase in x, you get what increase in y? 3. Or you could rewrite it as 1.5 over 1, right? Isn't that the same thing? So if you want to re-express it for every change in 1 in x, what change in y do we experience? 1.5, exactly, or 3/2. And also we know about two types of rate of change. There's average rate of change or instantaneous rate of change. Recall average rate of change is very simple. F of a plus h minus f of a all over h. And remember what it means graphically. I ran out of space here, so I'm just going to kind of do it here. You guys can use a quarter plane there. But let's say I got something really funky like this here. So that's A, and say it's B. Or sorry, A plus H. My apologies. So we call it the slope of what? What line is that called? Secant. There we go. That's it. That's all you're doing. So that's pretty straightforward. However, instantaneous rate of change is a derivative, right? Or it's a limit, limiting case. The limit as h approaches zero of f of a plus h minus fa all over h. Okay, it's probably drawing a very funky curve. So we'll call this A. And that's what's happening, right? So it's a, and that's not the best looking line. I could do a little better than that. A little better. Okay. Yeah. Now, can this line touch the curve elsewhere? Sure. They can touch over here or over there. But for a moment, it's just grazing the graph, right? In this vicinity, it's just grazing the graph. Um, and H, if you think about it, let's say A plus H is over here, but you're trying to get H close and close to zero because as H gets close and close to zero, those 2 points become one. When they become one, now it's no longer a secant line. Now it's a tangent line, right? So that's just to remember that. Now, let's think about this in terms of physics, in terms of velocity, right? The first case is an average velocity, right? Like from here to Los Angeles, right? 400 miles. It takes 5 hours. Your average velocity is 80 miles per hour. Do you drive 80 miles per hour the entire time? You do not. Maybe, or let's say that I'm sure anyone go to Tahoe over the break? No one to Tahoe?
Oh,
Okay, good. Do you get stuck in the snow?
yeah.
Okay. We're probably driving really slow, right? But probably before you got there, you're probably on Highway 80 heading towards Sacramento. You're probably driving fast, right? Cool. So that's what instantaneous rate changes. It's trying to find at that moment, like you're passing Sacramento, but then maybe you're going past like Truckee or going up the incline, and like you slow down a little bit, right? Um, and that's what we're trying to investigate. We're trying to investigate that stuff. Okay, so let's move on to the next page. Okay, so look at instantaneous rate of change for physical situations. In these situations, we will understand specific average rate and average instantaneous mean. So like let's look at a circle. Okay. Pi r squared. The circle is expanding, right? And actually this graph is off. Ignore those are supposed to be touching. Those are supposed to be axes. That's a terrible formatting. My apologies. So we'll let R be X, we'll let A be Y. Okay. And yeah, let's look at different values. So of course my area could change. It'll be pi, 4 pi, 9 pi. So what kind of shape do you expect here? Yeah, it'd be parabolic, right? Ultimately be parabolic. Okay. And of course, we're not going to look at negative R values because that's weird. We wouldn't do that. Now, if I want to find the average rate change from 1 to 3, okay. So let's see here. So you're really just finding this, right? It's kind of hard to draw. So it kind of looks like that, right? What would the average rate of change be? What would I say? What was that? Go ahead. Average rate of change. What would that be?
Nine.
9 pi minus pi over what? There we go. So it's 8 pi over 2 or 4 pi. Were units given? Yes. So we should state the units for sure. Um, Now the units are going to be a little funny. Um, so bear with me on this one. The units are going to be because the top represents area, right? What does the bottom represent? So it's actually going to write as this centimeters squared per centimeter. Let me give you an interpretation. Interpretation matters a lot. What it's saying is that for each change of radius length by 1 centimeter, the area changes by 4 pi square centimeters over the interval. So that's what it's saying. And that's something that really separates this class from other classes like pre-K honors or even non-AP calculus. They don't spend time interpreting. I have to kind of get you the thought process of interpreting. Because if you think about it, that's what's happening, right? Because you have a line that's a slope of 4 pi, but it means that every time the radius goes up by 1, what happens to the area? It goes up by 4 pi. So that's what you're saying. So I know it sounds weird to say centimeters squared per centimeters because that just reduces centimeters. But ultimately, we're going to be comparing this to time, right? Time's going to be on the bottom and distance is going to be up top. And of course, you can say miles per hour or centimeters per second or whatever, right? But for now, we have to interpret it this way. For each change in radius length of by 1 centimeter, the area changed by 4 pi square centimeters over the interval from 1 to 3. So that's how you interpret it. So now let's look at the derivative, right? Now let's do the instantaneous rate change, and let's see what happens there. And then we'll move on to the other parts of the problem. So what's my derivative going to be for if I do dAdr? I'll call it A prime, I guess. I mean, it's with respect to R. So what would the race be? What does that what does that look like? Circumference. So the circumference, well, it's or pi d. That's circumference. Circumference is the derivative of area. So if I plug in one, I get 2 pi, and it's just gonna be linear, 4 pi, 6 pi, 8 pi, 10 pi. So what do you notice about the values of dA over dr? They increase in a linear fashion. That's what we notice. Now explain words the difference between dA dr r equals 1 and dA dr over r equals 4. Well, what happens is that at r equals 1, sorry, you're going to say it, the area changes by 2 pi square centimeters at the instant when r equals 1 centimeter. That's what that means. Because the slope is not that steep at r equals 1. Is it more steep at r equals 4? 100%. So that's almost like acceleration in a way, which we'll talk about too. Because you notice that the derivatives are increasing. So the second derivative would also be positive, right? My second derivative should be positive here. By the way, what's my second derivative going to be? If I did the second derivative of this, what would I get? That's positive, meaning that the derivatives were increasing in value as well. And it's a little mind bending, but we have to talk about that when we get to velocity and acceleration. So for r equals 2, but can I erase all the other stuff? Okay, cool. So now it changed by what? 8 pi. It's kind of like if you blow up a balloon, right? Like initially, it doesn't seem like the volume's increasing that fast, but it seems to be increasing more quickly as it gets bigger and bigger and bigger, right? It's kind of the same thing in a way. But again, we're just doing a very simple example with area of a circle. Okay, we're good? All right. So now let's talk about position and velocity. And geez, this formatting's really messed up here. I think we'll be okay still. All right. So now consider an object moving along a line where its position s is a function of time t. Suppose s is measured in miles and t is in hours. What are the units for slope for any type of rate of change? Well, miles per hour, right? So the average rate of change in this context is going to be the average velocity, which is given by the following expression. And these graphs are kind of off. I need to look at the Word document because that just seems off to me. But it's given by the following expression. By the way, does anyone know the? Actually, I kind of gave it to you. S is used for position. So those who are taking physics, do you guys use that for position?
Use X.
X, okay, same thing. Doesn't matter. We'll use S for the sake of this class. So the average velocity is going to be written like this: S of t plus h minus S of t all over h. Because you're taking the difference in the two time intervals, or sorry, two time values. So, for example, yeah, I don't want to draw something just yet. Let's just talk about fill in the blanks because I'm trying to think of good examples to draw, but let's hold off on that. So, the instantaneous rate of change would be this: the limit as h approaches 0 of s of t plus h minus s of t all over h. Or we could think of it as s prime of t. That is what we call the instantaneous velocity. Okay, so where are the units for this slope? It's still the same. It's still miles per hour. Oh, sorry. My bad. My apologies. Um, we're now doing a different situation. Now we're doing the derivative of velocity. Okay, so if I do derivative of velocity, um, oh, by the way, let me fill the blank here. This is what we call the instantaneous velocity. Sorry about that. I was supposed to fill that out as well. So that's called instantaneous velocity when you do the derivative. Okay. So again, average velocity, like going from here to LA, 400 miles, 5 hours, 80 miles per hour. Instantaneous velocity, depending where you are in your journey. You want to find the velocity at that moment. That's instantaneous velocity. That's derivative or a limiting case of the average rate of change. Um, so now what if I do the same thing for velocity? So those units are going to be the following: miles per hour squared. So in this case, the average rate of change, we would write it like this. Gosh, they didn't really give us much space. I'm gonna do it down here. V of t plus h minus v of t all over h. And we call that I think that's what we put over here. We call that the average velocity. Hold on a sec. I just said that earlier. Average acceleration, my apologies. It also be thought of as like, yeah, just average acceleration. Then instantaneous rate change would be this. The limit as h approaches zero of v of t plus h minus v of t all over h. Well, this context would be the instantaneous acceleration, or v prime of t. Or you could think of it as s double prime t. Remember, s is position. So you take the position function, do the derivative twice, that'd be acceleration. So a good example would be with COVID, right? When people talk about COVID, the flattening of the curve. So people are still getting COVID, but if the curve flattens, is the rate of people getting COVID going up or down? Down, right? When the curve's flattening, people are still getting sick, mind you. They're still getting sick. So when they talk about the flattening of the curve, and it was funny because like it was, I was actually teaching calculus at the time, and I was trying to explain to people about second derivatives and things like that. So people are still getting sick over here, right? But are people getting, but is it getting worse or better? It's probably getting better over here at this point, right? But over here it was pretty bad because a lot of people, the infection rate was higher, right? So that's what we're kind of looking at for second derivatives. We're looking at like you're increasing, but sorry, it's position's going up, but is it slowing down or speeding up? For example, if you're going on El Camino and you see the cops, you hit the brakes. When you hit the brakes, are you going backwards or forward? You're still going forward, but are you speeding up or slowing down? Slowing down, right? We're gonna have this discussion on Wednesday where you have to look at velocity because if you consider velocity to be going north, let's say you're going north towards, like, say, Redwood City, cool, that's positive. But acceleration is working against you because it's slowing you down because you're hitting the brakes, right? But what if you decide to gun it, right? You gun it, what happens? You go faster, right? Um, so if you look over here, like that's the position function, right? Um, so if you, yeah, go ahead.
Wait, so like when the derivative is positive, then the second derivative.
Well, it depends. It depends. Like, so right now, my position, let's say I'm looking at like, actually, let's look at y equals 4 or t equals 4. It's pretty clear v prime 4 is positive, right? And my guess is that it's going to keep increasing. So sorry, I meant to put v of 4, not v prime 4. My apologies. I meant to put v of 4 is positive because that's because s prime 4 is positive because I have a positive slope there. The acceleration is a little hard to tell. Um, we'll have that discussion later. It's more about something called concavity. Um, but we'll worry about that later. I don't want to get into that today. This is pretty much as far as I wanted to go. I think I gave you guys a lot of information. I think this is great to kind of talk about. This snail problem is a really good problem. So I at least got you guys thinking about velocity a little bit and acceleration, but I'm not ready to have this discussion yet. So we'll do that tomorrow, not tomorrow, sorry, Wednesday. They'll look at the snail for example 3. We'll have a really good discussion on that. We'll talk about how it's going to look on the calculator, example 4. So these are good discussions to have because I don't want to rush right now. We got about actually, do you still have more time? Actually, we have a little more time. Hold on a sec. Hold on a sec. No, you guys want any more information? Need a break in life? It's okay. We'll stop there. No, this is good. This will be a good place. So let me tell you what the homework is about that. And you guys get head start on homework. Okay. I thought we were done by 12, but we're done at 12:10. Sure. So you guys get head start on homework. I think it's fair.
No, enough of that.
Um, what's what the last homework was? I don't remember. Okay, it's handout C 7 to 14. Okay. Okay, handout D.
Um, 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 oh,
It's fair. Yeah, you guys do handout D, number 1 through 6. That'll be your homework. Handout D, 1 through 6. You guys have access to in school, G.
1 through 6.
1 through 6, handout D. Yeah.
Point game. You're gonna see me jump off, my legs just do pretty full days. And what happens is you get tired from 4 to 5. What? And then David in the office.
It was his office.
All right, we'll stop there.
Sorry.